Hello, everybody. Today's topic are going to be confidence intervals. In particular, we are going to look at the definition of a confidence interval. Then we are going to see how we can calculate the confidence interval for a mean. And note that we will be make the distinction between two cases. The first case is the variance of the population is known. Note that this is a very unrealistic case, but I'm still going to use it because I can explain the basic concepts of a confidence interval. And then we are going to look at the second case, the more realistic one, where the population variance is actually unknown and we have to estimate it. We are then going to move on to the confidence interval for a proportion. A proportion means that suppose you want to calculate the number of people who are going to vote for the Democratic candidate. That would be a proportion. And then finally, we are going to look at sample size calculations. And we are going to look at calculation of a sample size if the population is infinite or very large, and the calculation of the sample size if the population is finite. For this exercise, we are going to use two data files that are necessary, and you can download them on Canvas. And the first data file is called gss.csv, which contains data from the General Social Survey, and we are going to focus on the year 2018. And the second data file is called meridianhills2.csv, which contains data about housing values in the Meridian Hills area. Okay, so the confidence interval is basically a range of values that is based on a sample such that the population parameter, that means either the mean or the proportion, is occurring within that range with a certain probability alpha. And we will see in the future that this probability alpha is usually 95%. Sometimes it is 90%, and sometimes it can also be 99%. But in most cases, it's 95%. We will see that the confidence interval is going to be a point estimate. Think about the point estimate as taking the average of the sample data plus a margin of error. Now, to put the confidence interval in a slightly different perspective, or explain it slightly differently, is that suppose you have a population and you take 100 different samples from that population. And then you're constructing a confidence interval as outlined in the future slides. And in 95% of those cases, the confidence interval will actually contain the true population mean or the true population proportion. Note that the population parameters, i.e. the mean or the proportion, will never be known. Okay? We will see that the confidence interval is influenced by three factors: the sample size, which we will call n, the population standard deviation sigma. Note that very often we have to estimate that population standard deviation by using S, and also the level of confidence, meaning if it's 95%, 90%, or 99%. Recall that the difference between the sigma and the standard and the estimated sample variance S is that in one case we divide by n minus n, and in the case of S we are dividing by n minus 1. Okay, so first look at the confidence interval for the mean. The components for any confidence interval involving the mean are two things: the sample size, so you have to know of how many observations do you actually have in your sample, and you also have to calculate the sample mean. On the previous slide, I called the sample mean a point estimate. Think about this if you are interested in the starting salary for MPA students. You take the average of all the MPA students that have graduated from the O'Neill School, and you calculate the average. That would be a point estimate of the sample mean. Now, the components, depending on what we know about the population, about the standard deviation of the population, actually determines of how we calculate this confidence interval. If we know what the population standard deviation is, then we take the sigma, and we can also use what is called the z-value for a given confidence interval. Note that the z-value is based on the normal distribution. If we do not know anything about the population standard deviation, or if that population standard deviation is unknown, then we have to estimate it first based on our sample. And this is where we are going to use the sample standard deviation, or the sample variance, which is calculated by dividing by n-1. And if the population standard deviation is unknown, we cannot use the normal distribution to calculate the z-value for a given confidence level, but we have to calculate what is called a t-value for a given confidence level. The t-value is based on the student's distribution, or the t-distribution. And I will explain what the difference is between a normal and the t-distribution soon. To calculate the confidence interval for the mean, we have to do the following. We first have to calculate the average sample. Have to calculate the average of our in our sample. Then we have to use the population standard deviation, which we may know, and we have to divide by the square root of n. Now, let me explain what this z-value means here. As you remember from the last lecture, we have what is called the central limit theorem, which says that if you randomly sample from a population, if you're taking multiple samples, then the average of the sample means is going to follow the normal distribution. Okay? So if we draw a normal distribution here, so here we have our bell-shaped curve. Then we have the mean here, or we call this mu. Then we said that the entire area under this curve is equal to 1. Okay. Now for the normal distribution, or for the standard normal distribution, remember that the standard normal distribution has a mean of 0 and a standard deviation of 1. Okay. Then what this means is if the mean is equal to 0 and the standard deviation is 1, then it turns out that we have a value here of negative 1.96, and we have a value here of 1.96, and those two values, those two bounds, what they do is they leave 2.5% of the entire mass of the distribution to the left, and they leave 2.5% of the entire mass of the distribution to the right here. Okay, so note that we now have what we have also then in the middle is we have 95%. Okay, so 95% is the rest of this entire area here. Okay, now note that this 95% is going to play a very important role, because remember that we are going to construct confidence intervals usually based on the 95%. And you will also see that the values of negative 1.96 and negative 1.96 are going to play a very important role in constructing confidence intervals, and then also in the future in constructing or in conducting hypothesis tests. Okay. So in the case of the confidence interval for the mean, we will see that this z-value here, if you want to construct a 95% confidence interval, that this z-value is going to be 1.96, okay, which corresponds to the negative 1.96 and the 1.96 here, okay. And I will explain why we have it, why we are going to use negative and positive here in a minute. Okay. Okay, so now let's do a more practical application here. So assume that you have the American Economic Association, which is the main association for economists, that they want to construct a 95% confidence interval for the starting salaries of economics majors. Okay, so those are undergraduates. And suppose that they're sampling 36 people that recently graduated, and they calculate the sample mean, and that sample mean is $48,500. Now assume, for whatever reason, that they know that the population standard deviation is $3,500. Okay. Then they are taking the point estimate of the starting salary, which is the $48,500. They are adding the plus or minus 1.96. Note that this represents plus or minus 1.96 represents the 95%, the bounds to the 95% area in the middle of the standard normal distribution. They multiply it by the population standard deviation 3,500 and divide it by the square root of the sample size n. This is what you are seeing in this equation here. So what they get is the 95% confidence interval, where they say $48,500 plus or minus $1,943. Okay. So as mentioned before, the value of 1.96 leaves 2.5% in each tail of the standard normal distribution, and so the $1,143 represents the margin of error. And the value of $583, which is simply the $3,500 divided by the square root of 36, which is 6, represents the standard error. Okay, so now this is the example where we assume that the population standard deviation is $3,500. Now, if you think about this, this is very unrealistic, because it is more likely that you would actually know something about the population mean than the population standard deviation. However, it serves as a good introductory example of how we have to think about the value of 1.96 or this z value. Now let's move to the much more realistic case where the standard deviation of the population is actually unknown. In that case, we actually have to estimate the standard deviation of the population by using S. Now remember that by using S, we are actually dividing by n-1. This matters if the sample size is small, but doesn't matter as much if the sample size is actually very large. Now, the approach is very similar to the construction of the confidence interval when the population standard deviation is known, that we have to divide by the estimate of the samples, the estimate of the variance, or the standard deviation, divided by the square root of n. But now we cannot use the z value anymore, but we have to use what is called the t value. Okay. Now the t value is not based on the normal distribution, but is actually based on the t distribution or the student's distribution. So just on a side note, the term student distribution comes from the fact that the person who actually invented this distribution, or who came up with the distribution, was working for the brewery Guinness in Ireland, and his employer didn't allow him to publish the paper under his real name, which was William Gossett. So in order to publish the paper anyway, he actually just chose the name student to publish the paper, and hence student distribution. Okay. Now, the student distribution is extremely similar to the normal distribution in the sense that the t-distribution is continuous, it's symmetric, and it's also bell-shaped. And the shape of the function, or the shape of the distribution, actually depends on the what are called the degrees of freedom. And now let me go back to the handnote here and explain a little bit what we mean by degrees of freedom. Okay? So think about, I give you three values, say x1, x2, and x3. And I tell you that the average of those values is equal to 5. Okay? Now, suppose I ask you, well, what is the value of x1, x2, and x3 when the average of those three values is equal to 5? Well, I could say that x1 may be 7. I could tell you that x2 may be, I don't know, 9. Now, I have picked those two values randomly. Now, knowing that the average is equal to 5, I know that the last value has to be equal to -1. Because if this wasn't equal to -1, we would not get an average of 5 based on those two previous values. So in this case, we have n, or the number of observations, is equal to 3. And the degrees of freedom, let's call it simply df, is actually equal to n minus 1, which is equal to 2 in this case. Okay? Think about this the following way. We have those three values, and we know what the average is, and we can pick, or we have the freedom to pick two of those values, but we do not have the freedom to pick the last of those values. Hence, the degrees of freedom is equal to 2. Okay? Now, the t-distribution depends on this value that is called degrees of freedom. Okay? So it turns out, and I will do some illustrations later, soon, that for very large degrees of freedom, mathematically actually an infinite number of degrees of freedom, the t-distribution is identical to the standard normal distribution. Now, the important aspect of the t-distribution are the tails, which are weighted heavier. Now, here I have a graphical representation of how the t-distribution compares to the normal distribution. Note that you have the normal distribution is the dotted line here, and you have the degrees of freedom, in this case very high, say 30. You see that it's very close to the normal distribution. However, if the degrees of freedom are very low, say 3 or even 1, then you see that the curve is slightly flatter, and you actually have more weight in the tails. Okay, so you have more area in the tails. For a given value, you have more area in the tails than for the normal distribution. Okay. Now, think about it the following way. Let me get back to this unknown population variance. If we do not know the standard deviation of the population, we have to estimate it. And think about this estimation procedure to add an additional source of error that we could make in calculating those confidence intervals. And hence, in order to correct for this area, we actually have to widen the area of the confidence interval to account for this area. Okay, so let me demonstrate this to you of how this actually works in practice here. Okay. Okay. Now again, think about the normal distribution. Let's make this in red. And now, so in red we have the normal distribution. And now let's take in blue, let's draw the t-distribution for a small number, or for a small value of the degrees of freedom. So we saw that it is slightly flatter. And it allocates more values, more weight to the tails. So what this means is as the following. So take this value of 1.96 that we know from the standard normal distribution, and this value of 1.96 leaves 2.5% in this area for the normal distribution. Okay. Now, if you compare this to the t-distribution, okay, so the blue line here is the t-distribution. Okay. So you can see now that for this exact same value of 1.96, we have additional area here. Okay. Note that the same which is true in this on the right hand side, we also have the same being true on the left hand side. Okay. So for a given value, say if this is negative 1.96, okay, then for the normal distribution we have 2.5% in this area here, but the t-distribution for the same value actually has a higher probability, or much more area in this area here. Okay. So what this means is the following: that if you want to construct a 95% confidence interval, and you don't know anything about the mean, and you compare, so you have the t-distribution. Actually, sorry. You have the t-distribution here. So if you want to calculate a 95% confidence interval, then you cannot use the value of 1.96, because for the t-distribution it would leave you more than 2.5% in this area here. But what you have to do is you actually have to move a little bit further to the right in this case to get an area of 2.5% in here. Okay. So note that if you're moving to the right, this also gives you, in many cases, gives you a value over 2. So your confidence interval is actually going to be a little bit larger than with the normal distribution. Okay. So the steps to construct actually the confidence interval for the mean, if the population variance or the population standard deviation is unknown, is as follows. You estimate the sample mean, which is x bar. You determine the degrees of freedom, and the degrees of freedom actually depend on the sample size, which is n-1, meaning if you have a sample size of 36, then the degrees of freedom is actually 36 minus 1 is equal to 35. Okay? So note, if you remember from the previous slides, if your sample size gets very small, then you're having more and more area in this. You're having more and more areas in the area in the tail, and your confidence interval is actually expanding, or this t-value that you are using to construct the confidence interval is expanding. Okay? Now, based on the confidence interval that you are interested in and degrees of freedom, you have to determine the t-value. Okay?
So to determine the critical value with MATLAB, you can type TINF, or t-distribution inverse, parentheses open 0.975, comma, and then the degrees of freedom, which is 35.
Note that I'm using this 9.75 because it leaves 97.5% to the left of this value, and it leaves the 2.5% that we are looking for to the right of this value. Okay? And then whatever value you get here for the t-value, you can be using the x bar, which is the sample mean that you have calculated before, plus or minus, because the plus or minus is for the lower bound and for the upper bound, the value, the t-value, times the standard deviation, the estimated sample standard deviation divided by the square root of n. So how this would look in reality? Now note that we have, again, the example about the American Economic Association who wants to construct the 95% confidence interval for starting salaries. They have the same 36 randomly selected graduates, and the average again is $48,500. But now assume that the population standard deviation is unknown. So before we said that population standard deviation is 3,500. Now let's assume that you actually estimate, based on those 36 random graduates, you estimate the standard deviation to be 3,600. Okay. Note that now you have to leave the $48,500 plus or minus a t-value of 2.03 times the 3,600 divided by the square root of 36. Right? Note that this value of 2.03 leaves 2.5% in each tail of the t-distribution with 35 degrees of freedom. Right?
If you want to calculate the critical value of 2.03 in MATLAB, what you have to do is you have to use the command TINF, or t-distribution inverse. You have to type in the probability that leaves 2.5% on one end, comma, and then you have to type in the degrees of freedom. In this case, 35. When you evaluate this, what you get is the value of 2.0301.
This is where this value here comes from. Okay? And very much like before, the value of $600, okay, which is 3,600 divided by the square root of 36, represents the standard error, and the $1,218 represents the so-called margin of error.
Now let us calculate the confidence interval for the home values of the dataset Meridian Hills 2.csv. Note that I have already loaded the data in MATLAB, and we have it here as MH2. Now in the first step, I am going to determine the number of observations, and I'm just using nobs, or number of observations, as the variable name, and I type in size mh.mh2, comma 1, and that will give me the dimension, or the number of observations. And the number of observations is 18. Then I'm going to calculate the mean of the data. Let's call this mean data is equal to mean mh2 dot the price, the mean of the price. And here the mean is $824,000. Now, in order to calculate the confidence interval, what we need is the standard deviation. Okay, and note here we have to calculate the sample standard deviation, which is exactly what MATLAB actually calculates. So let's call it stdef is equal to std and then mh2.price. And that standard deviation is now stored here. Okay. Then we have to calculate the value associated with the student distribution that leaves 2.5% on the in one tail. And let's call this T alpha based on the degrees of freedom. And as we have seen before, this is obtained by using the command tinf, by writing the percentage that you're interested in one tail, because note that since the student distribution, like the normal, is symmetric, that you can just go on one tail, comma, then the number of observations minus 1. And here you have the value of 2.1098. Okay. Now, then if we are calculating the lower bound and the upper bound for the confidence interval, let's first do the lower bound. We type in the mean data minus the value of the associated with the t-distribution times the standard deviation divided by the square root of the number of observations. And we get the lower bound of $564,000. To calculate the upper bound, we just replace the plus sign, the minus sign with a plus sign. And here we get a value of $1.84 million. Now, of course, this seems very burdensome to calculate the confidence interval in that way. Now, in order to make this simpler, what you can use is you can use the command t-test. Okay. Now, note that the command t-test, we are going to use this command later on, very often when we are talking about hypothesis testing. Okay. But for now, we are just going to use it to calculate a confidence interval. And now what you can do is you can simply feed in the data series that you're interested in into this command t-test. Now note that what happens to MATLAB, or what happens in MATLAB, is that if you are using a particular command, sometimes the command actually calculates a lot more output than is displayed. To access some of the output that is not displayed, you have to indicate the output that you're interested in parentheses or in squared parentheses. Okay. Now here, note that the command t-test can calculate 4 outputs, and we will look at those outputs later on. But the output of interest in this case is the CI, or confidence interval. So when we execute this line, then we can see that we have a confidence interval, and right here, which calculates the lower bound and calculates the upper bound. And note that the lower bound and the upper bound is exactly what we get from manually calculating the confidence interval. Okay, so this is much, using the command t-test is much simpler and quicker.
Now, calculating the confidence interval for a proportion or for a fraction is much simpler. Note that for proportion we have the following. We have the estimated proportion from the data, which we call p hat, and it turns out that the estimated standard deviation is p hat times 1 minus p hat, and then you take the square root of that term. So the standard error for the proportion is, let's call this sigma p hat, is the square root of p hat times 1 minus p hat divided by n. The good thing about the confidence interval for a proportion is that we can actually use the standard normal for the to construct the 95% or 90 or 99% confidence interval, and we say that the confidence interval for the proportion is p hat, or whatever the estimated proportion is, plus or minus 1.96 times sigma p hat. So assume now, as an example, assume that you're interested in the political party affiliation of voters, and you're sampling 1,000 people. And you find that 55% of the 1,000 people you sample are Republican voters. So given the equation on the previous slide, you can now calculate the sigma p hat by taking 0.55 times the 0.45 divided by 1,000 and taking the square root, and this gives you the 0.0157. Hence, if you calculate the margin of error for this, you have 0.55 plus or minus 1.96 times 0.0157. Note that if you calculate this term, that this is close to 3%. So what I want you to do, the next time you actually see any political poll on TV, think about, for example, voters that have to decide between Biden versus Sanders, or that have to decide between Trump and some Democratic candidate. That if the sample size is 1,000 people, which very often it is, then the margin of error that should be indicated on TV or in the newspaper or online should be plus or minus 3%. Okay, this is where this margin of error comes from. Note that if the sample size declines, that this term here also gets larger, and hence the margin of error increases. Okay? So I have seen polls online that have a very wide margin of error of close to plus or minus 5%. And then when you actually look at the sample size, you realize that the sample size is sometimes around 500. Okay, so it is a very, very small sample size, and hence you also have a very large margin of error.
To calculate the confidence interval for a proportion, we are going to use the data GSS, and in particular we are going to use the variable vote. And this indicates whether a person has voted during the last election with yes or no. Yes is indicated with a 1, no is indicated with a 0. Okay? So to do the calculations, we first determine the number of observations. And note that similar to the previous example with the Meridian Hills housing data, we are going to use the function t-test at the end, but I would like to go through the manual steps first. So determining the number of observations, you type in size, GSS, 1, and you find that there are 773 observations. Then you're going to calculate the mean of the data by using the function mean. Note that here you have to specify that you're interested in the vote. And you find that 67% voted during the last election. Now, you have to use the z-value, and which is the cutoff point of the normal distribution, which leaves 2.5% in either end. And to do so, we have to use the function normal function inverse. And we already know what the value is going to be, because that value is going to be 1.96. Okay? But here we have defined it. Now, to calculate the standard error, what we are going to do is we have to take the square root of the mean data times 1 minus mean data divided by the number of observations. And here the standard error is 0.0169. Now, to calculate the confidence interval is straightforward. So we first calculate the lower bound, and this is the mean data minus z times the standard error. So the lower bound is 0.637, and the upper bound, we simply replace the minus sign with a positive sign. And we find that the upper bound of the 95% confidence interval is 0.7033. Now again, we can actually use the command t-test for this. And note that in order to find the confidence interval, we have to explicitly mention that we are interested in a confidence interval. So we can say t-test GSS vote. Now note that we get the same values as before, the 6.37 and the 7.033. Okay, and so this is how you calculate the confidence interval for a proportion.